All right, I think we should start the lecture. So this time we will talk about model initialization and also ensemble forecast, which is a related topic. Okay, so what is data assimilation? Actually, there are some people who are dedicated to do this job. This is not just model initialization. It's about the performance of your forecast. So at the very beginning, the aim is, of course, is to fit your data. For example, here you have some time steps here. Right? If you want to work on the green dots here over time, but you only have observation over time here. Even the time is not in line with your model grids. So, and of course, this is the same for the spatial situation, right? You have stations here, for example, and then you have grid points like this, and you have to do interpolation. And the second thing is the most important. You have to do balancing. So by balancing, we are generating a best guess of the 3D atmospheric state. That's because if you don't have a good guess at the very beginning, then your error will propagate in the model over time. That's not something you want, right? And balancing is very important because if your original data is not balanced already, that will generate some waves, right? That will generate some response from your system. And you don't want that because that's not coming from the weather system, that's coming from the data, coming from the imbalance situation in your data, and that's not what you want. So the goal here is to estimate the state of your Earth system as accurately as possible. Okay. Two requirements. So the first one is to have the dependent variables defined on the model grid. Of course, that's the thing we want, right? Represent the conditions in the real atmosphere. So this is a satellite photo at analysis time. So you will know about this term analysis. We'll get to that later. It's very specific for atmospheric science research. Okay, and this is the initial condition. You need to put different variables, wind speed, temperature into your model and define on the model grid. Okay, and the gridded mass field variables, mass by mass field variables, we're talking about temperature and pressure. So you already learned about the stacker grid variables, the stacker grid case, okay, and momentum field variables are the velocity components. So they should be dynamically consistent. And of course, data assimilation is not just interpolation. Actually, they use these variables, the first guesses, they put them into the model and then run a little bit, actually, to find a balanced situation. And then that would be your model initialization. Okay, they do something to the data so that they are dynamically consistent with each other. That's the most important point, okay, as defined by the model equations. Okay, so here is just showing you the velocity components. Maybe if it is a tropical cyclone, then you should have convergence at the bottom, divergence at the top, and then rising motion in the middle, and that should be inconsistent with your pressure field here. This is the pressure field. So warm core low. This is a warm core low for a tropical cyclone. Okay, so the second requirement, so by dynamically consistent, we are talking about the different balance situation. For example, hydrostatic balance. You want to have a balanced data. So P here, the pressure here, if you don't want any signal coming from your data, you want that to be balanced with your gravity, okay? But you still want something that is coming from the true weather system, so that would be very tricky. Okay, and also geostrophic balance. It's so all the textbooks are written by the mid-latitude people, so that's why they put it here. Okay, it's not the case for our tropical region. It's not the case for Hong Kong also. Okay, so this is what it means by the initial shock, initialization shock coming from your data. So if your data suddenly you have some error in your one of the points, then that would create a huge change, right, with the surrounding. Then that would create some waves solely due to the error of your instruments. Okay, because your data assimilation guide didn't do a great job in doing the balancing, so that's why you have some unphysical signal. So they're not physical, they're not the real weather events, right? Unphysical waves will be overlaid. So you don't want that. And there is a period called adjustment period. Adjustment is, so you have to wait. So when I was a postgraduate student, the professors told us that the first few days of all the experiments are not considered because of this adjustment phase. We always throw them away because of this. Okay, even though the models are doing a great job these days, we still wait for a few days for your model to do the adjustment. So all the variables are adjusted to each other. And then you can use the data after that. Okay, so that's a recommendation from the professors or in the field. That's what people do. So and we don't want that, but we still want something in the model. We want the smaller mesoscale and convective scale scales weather system. We want them. So they should ideally exist in the initial condition. For example, there's surface heating. Of course, that's important, right? That's how we get convection. So we want the signals we want. We don't want the signals that are not physical. Okay. So there are different types of data. It's not perfect, okay, because we don't have data everywhere and at every time steps we want. So they are all irregular. You can see that some of them are in situ. In situ means in that location. For example, the weather balloon is you're measuring the temperature at that location. That's in situ measurement. And radar is remote sensing because you're not there. You are just sending some signal over some locations and then it bounces back. And you use that radio waves to sort of calculate the for example, temperature back. Okay, so that's remote sensing. So there are different types. Actually, most of our data are coming from the satellites, remote sensing. So already before you do the model initialization, some people have done some calculation to the satellites because you need to calibrate your data with respect to the in situ measurement. So they are referred to as the most accurate ones, of course, or the weather station data here. Okay. Okay, you can see that there are really irregular different types of data. Most of the data are coming from the land area, of course, because we live over land and it's cheaper to build the weather stations. And we also have some signals coming from the ships. So all the ships around the world, they are sending a signal. So this is the land surface data, a lot of data. So two things. If you look at these graphs, you notice two things. The first thing is that the southern hemisphere have less data, right? And that's not good, right? Because it's you want to have evenly distributed data points, but they're not, which means that the southern hemisphere is underrepresented. And the second thing is that the polar region are not really represented. So that's why people are arguing over the global warming signal is not that great because we don't have a lot of signal in the polar region. You can see that here. We don't have a lot of signal. And most of the heating actually is coming from the polar region. It's the coldest region in the world, so it's more sensitive to global warming. Okay, so you can see that so it's more of a pain to deal with this plus or minus 3 hour window because they're not measured at the same time. So some of the things here are measured at the same time all over the world. For example, this weather balloon and also the land surface weather station, but most of them are not measured, are not in sync over time. So we need to deal with that. This is telling you how we do the remote sensing. Right? We receive these radiances and we do the inverse modeling to find different variables, P, Q, and amount of clouds, for example. So we do this operational forward operator. So it's a fancy word. It's just inverse modeling. Okay, finding these with the signal that you receive from the satellite, for example. Okay. We need to guess different variables for different levels here. So the number of levels should be less than the number of levels in the model. Okay, this is inverse modeling. So by the model, it's not the abstract model, it's this inverse modeling. Okay, we'll get to that in lecture 12. Okay, so it's pretty easy how we fit the data. So this is one of the methods. There are many, many methods. So let's say if you are here, okay, this is one of the model grids. So the circle ones are the model grids, right? And then here are the squares are the stations. So how do you guess the variable in here with the data over the weather stations? Because you don't have a station here, right? How do you guess that? So basically, we are fitting a curved surface. The curved surface should contain all the points in here. So the height here is the values, okay, the height of the surface here are the values for your variable for this region, okay? And then you use 1, 2, 3, 4, 5, 6, 7, 8. Use the points here within a region to fit this curve, okay? After you have fitted the curve, then you can have the value over here, right? You just substitute X and Y, and then you can find Z, the height here, which is the value of your signal here. So basically it's that without the math. So with the math, it's just fitting an equation like this, right? You are a surface, so there should be 3 variables, X and Y, which is the horizontal location, and then Z is the value, is the variable in terms of X and Y. Okay, and this equation is represented by this mathematical expression. Okay, and the big circle here is the circle you want to refer to. Okay, that's depending on you. So I know you like physics, but sometimes we need to have something arbitrary or decided by you. Okay, decided by people. So it depends on the people who do this data assimilation. So we have decided the area, and then we fit the curve. So use the observational data to find the 6 coefficients. So it comes down to this, to find the C's here, 1, 2, 3, 4, 5, 6 of them. And then you can decide the surface shape, okay? You decide the surface shape. So there are different kinds of fitting. I'm just showing you what it means by curve fitting here. So these are just a line, but this is a surface. Okay. Okay, so how do we do the fitting? So for each of the observational station, the square, for example, here, you want to use this. Okay, how do we use this one? So we do the subtraction first. So this is your polynomial here, your surface here, and then you subtract that by your observational data. Okay, so the surface here, subtract your observational data, it should be very, very small, right? If you have a good fit, it should be very, very small. You want to do the subtraction, and then the distance between these two, of course, it's not just distance, we put a square in here, is I. So you want to minimize I. So this is a very standard procedure statistically. So you want to minimize I, and then we want to minimize I by setting the derivative of I. So we differentiate I against each of the coefficient here. 1, 2, 3, 4, 5, 6. So we have 6. So just differentiate this one over each of the C. Okay, and then you get this. And then we set this to 0 because we want I to be minimum. Okay. It's pretty standard statistical procedure to find the coefficient. Okay, and then now we have, because we have 6 coefficient, right? 6 C. Yeah, 6 coefficient. We have 6 of these, and then we can set up 6 of the equation here, or this one. So this is more this is clearer comparing to the above one. So the first one is for the first coefficient, C00, and then second one is C10, right? And then they should be here multiplying this one. So this is matrix operation. And then at the end, you will have this, the thing on the right hand side here, which is you just take one of the term and then put it on the right. So the green term here is just the term here multiplied by C, right? You take it on the right hand side. And this is how you find, because all the things here you know, and then all the things here you already know. It's coming from the data. Okay, and then you can find the six. So you can think of it as 6 equations, 6 unknowns. It's pretty easy. Okay. We'll get to the, actually we'll do this inverse modeling. It's called inverse modeling. Actually, it's just matrix, something matrix operation in week 12. This for this lesson, this is not the main dish. Okay, so this is one of the methods for data assimilation, and this is also still least square method, so still the similar statistical process. Let's say we have 2 independent observations, T1 and T2, 2 temperature, maybe from 2 different devices of the true temperature, this one, the true temperature here. So they are in some way representing this true temperature, but you have some errors, unknown errors, and we consider them to be unbiased. Yes, here. Assume the measurements are unbiased. So by unbiased, we are talking about here. So the average of the average of your error should be around 0. So there should be a distribution of the errors. Okay, so the expected value of error, T1 minus your true value should be the error, right? T2 minus true value should be error for the second device. Okay, and it should be 0, which means that they should be around, they should appear around this 0 value. Okay, And we know the variances of observational error. So the this is, so we need to know the expected value. We need to know the error, right? We need to have a representation of the errors for both of devices. And we also need the variances of the errors here. We, of course, why we want the representation of the variances here, because we want this to be very small, right? If it's very large, it means that your devices is not giving you good measurement, right? It's giving you a very large deviation. Fluctuation is large from your true value. You don't want that. So that's why we need to have this. And we assume that they're uncorrelated. They're not coming from the same measuring mechanism, okay? Statistical information, these are the statistical information that we need about the true observations. Okay, so the next is to look at them as a linear combination of the two. Okay, so this is your guess. TA means analysis. Okay, we want to put this as the initial condition. So this lesson is about initial condition of the model. So A is what we call analysis, is still not the true value. Of course, we'll never get the true value, right? And so it's a linear combination of your first and your second devices, both devices. Okay, and the analysis TA should be unbiased. So we still think of it as the unbiased value, okay, comparing to your true value. So A1 plus A2 should be 1, of course. These are the weights for each of your measurements, okay? And TA, the analysis, the temperature analysis will be the best estimate of your true value if we minimize the mean square error, of course. We have the variances, the variance of your analysis, and then this is the expected value of your error. Okay, and then after that we could find A1 and A2 so we do the same operation by minimizing the variance with respect to the coefficients here, just like the previous slide. So we want to minimize this one, okay? And then we can find a specific representation for A1 and A2 in terms of the variance of both of your devices here. Okay, so this is supposed to give you, so if you have the variances of the error coming from your device, you are supposed to combine the measurements of the two devices with the minimum error. Okay. Okay, so next, we don't just do data assimilation at the beginning. Sometimes we do continuous intermittent, just the same idea. Okay, intermittent assimilation. So here is a timeline for data assimilation. So we start, sometimes when we do forecast, we don't just do one simulation, right? We do a lot of different simulations and compare the results. Okay, so we start the first one at this time, and then that would go a long way to the future. And then the second one, for the second simulation, the green one, you do data assimilation at first, collect the data within a time window. Okay, and then you start your simulation 6 hours later. Okay, and then so on and so forth. Okay, why do we do this? We'll talk about that in this section. Okay, why do we do? Okay, we only have one reality. Why do we do so many simulations? That's because our model is not deterministic. Okay, the world is deterministic. Our tool is probabilistic, actually. We'll get to that idea later. Okay. So assimilations at the time that the observations are made. And we do what we call Newtonian relaxation, or just the simple term called nudging. We always use this term, nudging. So nudge, what is nudge? So this is the elephant mother nudging the kid. So it's just like this, a little bit of push. Okay, it's an empirical method. We're not proud of it, but this is how we get the better weather simulation because of this. So it's very, very simple. We just add another term to any term you want. So any equation you want. For example, this is the momentum equation. We add a relaxation time, which is this one. And this is what you measure. So this is how we do the nudging. For example, every time we do nudging, you put the observation here and then minus by the original value that you're guessing here. You want to get here. So the larger the deviation, the larger the term, right? The larger you're pushing this u towards the observation. Okay, and this relaxation time is something you choose. The modeler has to choose. If it's very small, then your solution will converge to, your solution will change to this observational data too fast, and the dynamics got no time to adjust. So you have shock coming from your model also. And if it's too large, then that's no good, right? Your model less influence from the observation. So you have to choose suitable relaxation time for your nudging. Okay, so here is further explaining what it means by doing multiple simulations. So here you have what we call analysis. It should be coming from all the data handling after you have got the measurements, right? We call that analysis. So it should be your initial condition. You analyze all the measurements and then you put that into your model as the first time step. Okay, initial condition. So you initialize the model here, and then we do one simulation. And then we use that to okay, and then so here analysis, just statistical interpolation and balancing, and then initial condition, or if it's a regional model, you need the boundary conditions of the full model. That's not important. Okay, and then you have the forecast model. You do all the dynamics here, and then you use that as operational forecast. And in the meantime, in the middle of your simulation, you will take this forecast output, the output of your model, and then put that back as the background, as the analysis. Okay, of course, you need to combine with the observation. So this is just telling you the same story over a timeline. So we here, this red line is supposed to be this one. So it should be the output of your model, not here, not at the beginning. Output somewhere, and then it will combine with the observations, which are here. Okay. So it's what we call the 4-dimensional data assimilation. It's very standard in weather forecast, actually. So there are different types. So on the right-hand side, what is the main difference here? The main difference is coming from here. So if your regional model, you use the analysis, regional analysis, of course, from the model output and from the observation, do the statistical interpolation and balancing. And then you also use you also need boundary condition, where you have a boundaries for your regional model. So you need the boundary conditions on the global model. So that's the only difference comparing these two. And also the time here, of course, regional model, you are focusing on shorter time scale. Okay. So what does it mean by data poor region? So of course, over the ocean is data poor region. So this is an example showing you. So sometimes we rely on the location where we have a lot of data. Right here, this is the data rich region. And if you have a synoptic scale structure, for example, along here, and it travels to the data poor region. So the signal affected by the system will appear here as the first guess. So we know that this signal might be good because the signal is coming from the data rich region and you have already done the data assimilation. Okay. So sometimes we do this. Okay, remember the analysis term. So you have the analysis, which should be a combination of your background forecast and also the observation, right? So you can see that the green dots are the observation. You combine them, do data assimilation, and then you run a background forecast at the same time. So you don't give this up. You know that this is it has a deviation, it has a large deviation from the observation, but you don't want to give it up because you want to do the combination of the two. Okay, so this is how we do. So ensemble of 10 assimilations over 24-hour simulation window. So you are doing data assimilation over this window. Okay, so this is the same operation we have just talked about. We start a forecast. We start a forecast over a day, and then we start another forecast for another day. So in the Second World War, they did this also. They start the forecast at the middle of June 3rd, 1944, and then they got the forecast of the 5th on the 4th. Okay, one day before the day you want to forecast, and then they start another one. Why were they so fixated on this period? Because they need full moon, they need the light, right? They need low tide, and they need light wind and low seas. So some of the things they already knew, right? The tidal wave is very much known at that time. But little cloud cover, that's something that they didn't know. Okay, they need to do weather forecast because they want to get Europe back. Okay, so the full moon was on and low tide was on 5th to 7th. So that's the time window they have. And why did they do another forecast before that? Because they want to see if their method was good enough. Okay, if you're sitting here and you know that, okay, the previous, if you're sitting here, you know that your previous forecast was good because you are already here, right? You know that your previous forecast is good. So they do another forecast, and then they have decided to go ahead and then go back to get you back on the 6th. So that's how they decided the D-Day to be June 6th, 1944. Okay, so the same operation here. Of course, they didn't have data assimilation. Okay, there are a lot more different methods to do the estimation, so do this data assimilation. So very similar to the previous method that I've mentioned. this is an empirical approach. This is not statistical approach like the one we have introduced before. So empirical approach meaning that you are putting the steps here and then putting that to your computer, and then not just computer, you can calculate by hand, but it's like some steps you follow so that your data here will be your first guess. The data here will contain the information around you, the station here. Okay, so how do we do that? First, we estimate the gridded field, which is given by the background here, this one. Background meaning it's coming from the background forecast, which is this one. Of course, it's not the true value, or it's not close to the observation, right? But it's your first guess. Okay, first guess here. And then it's your 0 iteration. So the index here is the number of iteration, the first or the 0 iteration. Okay, and then we do this to move forward to the next iteration. So n, this is your current iteration, and then n plus 1 is your next iteration, much like what you do with the numerical the numerical methods that you have learned. Okay, so this one is your observation, this one is your current iteration. If you start with 0, then this one is f0i here. I is the index, so k here is representing different stations here. Okay, and then we do this summation for all the stations. For example, here you have 3 points, so you do this 3 times, do the subtraction, and then multiply the weight. The weight is decided by the box here. Okay, and this is another weight, and here this is the error variance. So if the observation is perfect, then your variance of your error should be 0. Okay, so of course it's not 0. Okay, and then this is this is an empirical approach. There are a lot of things you need to decide. For example, the circle, right, and the weight here. You can calculate the weight here by the ratio between the large circle and the distance between these two. Okay. Okay, that's how you move forward. So you get to decide how many iterations you do to force your data to be influenced by the data coming from the weather stations here. Okay. Any questions? It's pretty straightforward. So if you want to do, for example, you want to do the successive correction method, you just follow the steps here. Everything here is known already. Right? R, big R is the distance, small r is this distance, and this one is the location marked by this blue cross, and then this one is the location marked by this circle here, the yellow circle, right? So, all you have to do is to decide how many iterations to do. So every iteration makes the estimation closer to the observation. So you have to guess the value in the orange dot here, and then you make using information within this large circle. Okay. Why do we do this? It's simple economic provide reasonable analysis. So we need to get the value here so that you can put into your model as the initialization. Okay. And if you use this one, then you have to control this, because you need to force your analysis to closer to the observation. And so there are different choices you can make when you do data assimilation. Okay, next is what we call a cost function. So we calculate the difference between your between the true signal here and the observation, and the true signal here and the background forecast. Right, the two, you only have two things here. If you look at this, if you look at this graph, you only have two things here. The first thing is the background observation, and the second thing is the observation, right? You have the B and the O. You have to find the analysis status, which is this red line. So we want to calculate something called cost function, so the distance between them divided by covariance. Okay, and we want to make this as small as possible because this is representing the distance, right? So differentiate J, again, the same operation, differentiate J with respect to T to find out the minimum cost function. So we want to minimize J to minimize the error. Okay, so it's the optimal combination of the two pieces of information. It's not just a linear combination. So here we calculate the cost function for your analysis from the observation and then from the background forecast here, which is the forecast you don't want, the previous forecast you don't want. This is the current forecast, which could be the previous forecast or your next forecast. So we do this indefinitely, and we continue to rerun the model to minimize the error. Okay, there are other methods. So this is also another method. So we combine the first guess, the background, and the observation. T1 is background and T2 is observation. So we rewrite the equation analysis, which is something we want to put into your model as the initial condition, right? And we make use of, first of all, the background forecast and the observation here. And this is what we call the optimal weight, something you decided with the variances here. So this is how we combine the two, observation and background forecast, as the initial condition. I think this is pretty straightforward. I'm repeating myself actually. This is optional, so I think I'm not going into the details of this slide. I'm just skipping this slide. It's pretty boring actually. When I read the book about the data assimilation for this lecture, I was really bored. I just picked the things that seem showing you the concepts, and then I'm skipping all the details because it's really, really boring actually. Okay, so this slide is like a history lesson for you because this is the first person ever tried to do the weather simulation. I don't know if you have watched the video that I've sent you a long time ago. Okay, this is the YouTube video. So Louis Fry Richardson, he attempted to do numerical weather forecast in 1922. So here are the details. So he tried to do the weather simulation for Germany. Okay, so what he had is the upper air observations. So he already had the upper air observations. He already had the weather balloon. So I guess it's weather balloon, or yeah, he might have done the weather balloon and pull them back because they shouldn't have the remote sensing back then. And then each of the grid boxes 3 degree longitude, and okay, something is covering it, sorry for that. And each of the column was divided into 5 layers. He even had vertical layers in his model, and he failed epically. Why? So this is the number that he got wrong here. So the partial t he calculated is 146 hectopascal, which is really not reasonable, right? And in reality, essentially, so this is almost like 0 in the surface pressure, but this is what he calculated. So the thing here is that he has used full primitive equations. So he didn't use any approximations. All the terms that he had, he put them into the model. And it turned out that some of the things are not balanced at the beginning. So he didn't do the balancing. He might have done the interpolation, but he didn't do the data balancing in the model. And then some of the signal are not balanced with each other. And then that's why he calculated such a huge number in the pressure change over time. And that's why I introduced this story in this lesson, because this lesson is about model initialization. So that's why some people in the mid-latitudes, for the mid-latitudes region, some people invented or they discovered the geostrophic balance. That's because of this. So if you balance all the things in the equation and put them in geostrophic balance, and then use that as initial condition, that could get rid of a lot of small scale noise. That's why people like it so much. Okay, so dynamical balancing initial condition. So this is how we see the data, the model simulation. So at the beginning, a lot of things are not balanced, coming from the unbalanced situation in your data. They are fast moving gravity waves. So you don't want to introduce gravity waves in your model at the beginning, which are not physical. Okay, maybe the physical ones you like them, but you don't want the unphysical ones. So it will not affect your slow varying weather events sometimes. So this is the slow varying event. So things happening in the atmosphere are pretty slow. Of course, it's not slower than geology, okay, but it's pretty slow, because you can see that today's weather we have a higher chance to have the same weather as today for tomorrow. So this is what we mean by slow, okay? So we expect that things will be balanced after about 1 day. To be safe, I would say 2 to 3 days, okay? And this is not true. Actually, they interact with each other, right? Waves, they interact with each other. So we don't want this. So we want to reduce the small scale signals as much as possible, okay? So that they wouldn't superpose with each other, okay? So this graph is showing you the dynamical balance in the initial condition. So this is a graph showing you there's a jet here, wind flowing from the left-hand side to the right-hand side, and there is a jet maximum. So if this is a jet, then should be giving you a very high velocity of wind, okay? And you have a jet maximum, and then you have some height levels in here, and assumes we have geostrophic balance. And if your wind goes from location 1 to location 2, what happened? Okay, so the change of your height is larger right? If you look at this in this manner, it's not just x, it's horizontal distance, okay, horizontal distance for your change of your height, okay. So this is larger than your model will responses either. So there are two responses your model could give you. The first one, so if this term is larger, then your win could be larger. Okay, I think I put down the wrong equation here. It should be partial, should be this one. Okay. So your pressure gradient is larger than your win is larger. The win is larger. Or your pressure gradient can move away, thus weakening the pressure gradient at 2. Okay. So it is like a fight or a battle between the gravity waves and the inertial waves modifying the wind field. So your model will respond with either way, which means that your model can respond by changing the speed or changing the height field, right? Your mass field can respond to the change, or your momentum field will respond to the change. So how do we decide the relative importance? The two types of waves in here, two types of physical processes in here. We have already talked about this a few weeks ago, right? Geostrophic adjustment. I guess you already know about this. Okay. So anyone who needs to take a break? 有冇人啊？冇人，我繼續講啊。Okay, let's go ahead. So the next part would be about ensemble forecast. It should be a topic covered actually in this course. So I think some of you have taken the statistical course of ESSC4520. We have used this textbook. The new one doesn't have this cover. Actually, this is the old version, which has a cover looking like this. So this is pretty standard in studying atmospheric science. So it's telling you the deviation from the initial condition to different states. So if the circle is representing the states of the atmosphere, then over time, so the horizontal distance here is representing the time. So over time, your states will deviate from each other, even though if you start with very similar initial states. So they've used this as the cover. I think this one is much better than the new book cover. We'll get to the details of this in this part of the lecture. I know why you think that, okay, this is talking about simulation, numerical methods. Why is it on the cover on a statistical method book? You will know about this later. Okay. So there are many systems that is the state of your system, or your final appearance of your system. It's very sensitive to the initial condition. It turns out that we have a lot of these systems here. Okay, we have a lot of systems in, and also atmosphere is also one kind of the systems. So for example, if you put a pin in here and then you just throw a ball from the top, there's no way to predict the motion of your ball, because okay, maybe the physics is pretty clear, right, about this, but your how you put the ball on the top of this pin, there are many ways, and the many ways are pretty much similar, right? You just put it above the pin, but you cannot predict the pin, because a little bit of the movement when you release the ball, a little bit of the difference when you release the ball then you cannot predict the movement. Also, a pencil standing on its pawn. So the physics is also pretty much known, but there's no way you can put the pencil standing on its pawn, and it's always falling to the direction that you cannot predict. Okay. Also something what we call space balls. I don't know if you have seen this kind of toys in the shops. Okay, so you have two balls in here, they rotate around this axis, and then you have another ball which is pulling them from below, and this axis is allowed to rotate also. Okay, so I have found some videos, but I don't think you need me to show you the link. So I found some videos of this space balls or space trapeze. Okay, it's very amazing that they never move in the same way as before. Okay, and also the double pendulum. So the two pawns here that are allowed to rotate. Okay, I have a YouTube video here, and also I've read this from the book, the Rand's water wheel. So this wheel is turning according to the center of the weight of the whole system. Okay, it doesn't just turn one way, it's allowed to turn freely. So you have water coming from the top, and all the buckets, they receive the water, and then some water is getting out of the bottom of your bucket. So there's a speed here, right? And it turns out that they would rotate back and forth according to the center of weight of the system. And it's pretty what we call chaotic. So all the system here are called chaotic systems. So I think you should watch this first video about the butterfly effect. I think all of you have heard of it. And the second one is quite beyond the context of abstract science, I guess. It's because people have went on from just studying the atmosphere to other things. So this is the second video. It's about this equation. It's giving you the chaotic behavior. And they study the logistic map. So it's way beyond this, the context of atmospheric science. And I'm no expert in this area. I'm just introducing this in the context of atmosphere. And if you are really, really interested, you can read this book. They have a lot of different examples, and of course with equations. And you can look at this book if you're interested. But for this course, just the first video is good enough. Okay. Okay, so one day in the winter of 1961, Edward Lorenz, which is the scientist who sort of discovered the chaotic system or chaos, he started a simulation midway. So he went out for coffee. He rounded the numbers. So the numbers were 6 digits in the computer, and he rounded the numbers and put them back because he wanted to save some time, and then put them back as the initial conditions. And the model had 12 variables representing the weather state. So he found that his original run doesn't give the same result as the run that he has just started. Okay, so the new one and the old run, they don't match with each other, even though they start with he thought that it's the same number, right? They are pretty much the same. One with the rounded numbers and one with the original 6 decimal place numbers. Okay, they're not the same. And then he checked the computer, and the computer didn't break. So, and then he found the chaotic behavior of the system. And then he turned that 12 equations. Of course, he had 12 variables. He had 12 variables in this simulation. And then he simplified the system into 3 equations to show the butterfly effect. So the 3 equations are shown in here, X, Y, Z. Actually, it's I've taken this from fluid mechanics books. So it's actually showing you a case where you have differential heating in the vertical sense. So you have temperature, lower temperature on top, high temperature on bottom, and there should be convection according to the viscosity, or also the thermal diffusion of your system. So there are a lot of videos about this. It's called Rayleigh-Bernard. Do I have the term here? Okay, for more you can read this, but this is not important. I'm just showing you that this is similar. The simplified system here is similar to the weather, actually, similar to the weather. It has a chaotic behavior. So the three equations here, the first one is the convective flow. The second one is the horizontal temperature distribution. And the third one is vertical temperature distribution. So we have a 2D situation here. Why do we just have one variable representing the flow? Because they have turned that into a stream function. Okay. If you don't understand this, don't worry. We'll not go into the details of this. So, and also if you remember the Boussinesq approximation, we have separated the temperature or a lot of different variables into the vertical distribution, right? Vertical distribution, it doesn't change over time, and also the prime terms, okay, the bar terms and the prime terms. So we can separate, it turns out that we can separate temperature into two components, right? So this is what it means. So under the Boussinesq approximation, and also we turn the flow into a stream function, we have three equations representing the system, the convective system here, and coefficients which are controlling the behavior of the system. If your coefficients are not right, it means that your viscosity is not right. Okay, so the first one is sigma here, the Prandtl number, which is we have talked about this in 4210, I guess. So the ratio of viscosity to thermal conductivity. So there are two ways to have heat conduction or heat transfer in here. The first one is by viscosity. We're talking about convection, the overturning. The second one is the conduction, thermal conductivity. So it's the ratio between the two heat transfer Prandtl number. And the second one is the temperature gradient, which is something you control in the model. And B is the ratio of the box width to the box height. It turns out that the size also matters too. So we have to have the right coefficients to see the system running, and also the chaotic behavior. Okay. Don't worry about this. So the two boxes in the gray is supposed to be optional. And also the lengths here are optional. Don't worry about this. So if you don't understand this, just think of the atmosphere represented by three variables in here, X, Y, Z. So I have plotted this. Sorry. Okay, so I have plotted the result of the two simulations. The result of the two simulations in here. The red one is starting with X equals to 10, Y and Z equals to 0. And then the second one is 10.1. Okay, just a little bit different from the red one. So they have very, very similar initial conditions for the two experiments in here. So they are all starting, both of them starting from here. Okay, you can see that they are pretty much having the same trajectories in the XYZ plane. the three variables. Okay, and then they start to deviate over time. Okay, and then they deviate more and more until they're not the same anymore. Okay, they have totally different states and totally different trajectories. Okay, so this is just showing you the idea. So the butterfly effect, the so-called butterfly effect, the butterfly is coming from this XYZ model. So it's not the true climate model actually. Okay, next slide. Okay, so it turns out that we should see the simulations in this way. We should see the simulation, we should see the initial condition, for example, this temperature variable with a range of states in the beginning, in the initial condition. And then we start different simulations and they should give us a range of results. And we look at it statistically. That's why it's on the cover of a statistical method book, because it's finally it's also about statistics, right? So we describe the state operator with the range of values here in the initial condition, and incomplete observations and uncertainties and errors in your initial condition will have some effect in your simulation and they will deviate. So we have a set of deterministic runs. So they all give you one reality, right? So there are different realities here, the model realities, which is not the true reality, right? The model realization. And we have resulted, so it resulted in a range of future scenarios, so different scenarios in here. So the example here is the European, they use 51 ensemble members. Why is it 51? So the one is the one with the best guess, best analysis, best initial guess. And the other 50 is just for comparison, right? Or of course what they give you is the ensemble average. Finally, actually, they have done some statistical calculation to the 51 ensemble members, which means that it's not that they don't trust the control one, because they should have some idea behind the uncertainties, because if you have 51, then you have a range of uncertainty. Okay, so let's say this is how they study, sometimes how they study the 51 ensemble members. They separate them into different groups, just like what we do for the tropical cyclone tracks, right? Sometimes they form groups. For example, this one, this is a group, and then this is another group, this is another group. You know that you don't know which one of them is true. Actually, maybe none of them is true, but most of the times we just average the ensemble. That's why we call it ensemble average. Sometimes they separate them into different groups, not just by one variable in the last slide, but by the shape. For example, here they are forecasting, of course, the mid-latitude people, they like to forecast this synoptic scale pattern, right? That's how they get the winter storm, and for the Europeans, they don't have, I think they don't have tropical cyclone, so they care about the winter storms. So that's why they look at the synoptic scale graph here, and then they group them into, they put them into different groups. So cluster here, different clusters, cluster number 2, cluster number 3. So it depends on the shape, for example, of your pressure levels in here. 2, right? 2. And then they study them. Okay. I have some links here if you're interested. And we also do spaghetti plots. So here are the results of all the ensemble members. And what we do is that we pick one feature which is very representative in your model. For example, here, they pick the 5520 meter contour, the height contour for the 500 millibar height field. They pick that and then they draw that for all the ensemble members. This is actually a US model, it's not European model, but it's the same idea. Okay, so the first graph is the forecast for 12-hour, 36-hour, and 84-hour after initial time. And the thick line is the verifying analysis. The thick line is supposed to be there for you to verify your results. Okay, and you can see that for the first one, well, why are they so close to each other? It's because they agree with each other, right? The only place that they do not agree with each other is this in the middle of Canada. Okay, and then after a while, you can see that your model is not getting a good result for this feature. It's not guessing, it's not giving you this feature, right? This is for comparison. This is coming from the observation. It's not, we don't call this observation, we call this analysis, verifying analysis, because it's a combination of different things. Okay. So there's deviation, and there are some models capturing this feature and some models they don't. So this is how we study the physics, right? We know this is the place where we don't get the feature, and we can go back and study. Maybe it's coming from the observation. So we might have to do better observation upstream here, because this is the place where they deviate with each other. Okay, we might be doing some, we might be redoing the simulations with better observations. Maybe we can get this feature. So after, of course, after 84 hours, it's really not it's really not following the reality, right? Your model is not giving you that. So it's all coming from the initial deviation in here, so we don't want that. Okay, so uncertainty is coming from upstream here. Maybe it's the physics, maybe it's the data, you don't know. So you redraw this graph, these graphs to find out. Okay, this is the graph that I've shown you at the beginning of this part of the lecture. So we have initial condition with some uncertainty, and then we start. So this is the analysis. We start the simulation, which is a deterministic forecast, and we start other ensemble members. It should have some very small deviation from your analysis. Okay, and then that will give you the forecast uncertainty here, and it should be within the climatology. Climatology means the range of states that we could have in the atmosphere, and that sometimes that would, some people suggest that that would create a problem because the climatology is shifting also because of global warming. Okay. Okay. That's it. So the first question is pretty easy. I'm not going through the details of this. Okay, and the second one. For the second question, you have to do simulation for the Lorentz model. I've given you the sample code in here to calculate all the trajectories in here, starting from this initial condition. Okay, and you need to change that to use this the scheme that I've given you here. This is a third order scheme. Okay. Answer the questions. There are different questions in here. Any questions? That's it for this lecture. Okay. Okay, what is the data assimilation textbook you mentioned? I have actually used different textbook, different literatures for this lesson because all the books are they don't have I don't think they are really comprehensive enough. Either they are too intensive in terms of math, or it's too much text, just text, no math. And I think I've put down the books somewhere. Are you sure about this? I don't even want to read them. Really boring. I think here, this one. Okay, it's coming from this book, this method. But there are also other books. This one. They have a chapter, I think, for model initialization. Yes. Can I ask what is deterministic forecast in page 40?你揾翻啲 link 翻，我又擺喺個 slide 度中間。40. Okay. So just ignore the forecast word in here. Deterministic means that it's describing the reality, right? We only have one reality, unless you believe in some parallel universes thing. We only have one future, right? So it's deterministic. But when we talk about deterministic, it should be deterministic versus probabilistic. So the reality is deterministic, and our tool is probabilistic. So we give you the tool, the numerical simulation is giving you a range of the future scenarios. Okay, and this deterministic forecast, we shouldn't do deterministic forecast because our forecast has uncertainty. So this is like the reference forecast. You don't need to worry about this. So this is like the one reality starting from the best guess. Even though it's the best guess, we don't just use the best guess to do the simulation. Okay, so there are even though if you use the best guess to do simulation, it doesn't mean that it will give you the best results because you already have studied the numerical methods, right? It will give you a lot of error in the middle of your simulation, not to mention the uncertainty starting from the beginning. So in the middle, even if you stop the run and then you restart the run, that would be different from the situation where you continue to do the simulation. So we shouldn't do this. We shouldn't do deterministic forecast. We should do the range of forecast, or the ensemble forecast. So don't do this. We should do the ensemble forecast. 好唔 OK 啊？解唔解到啊？ You know, when we do the atmospheric science research, we buy a supercomputer and then run the simulations on that computer. If that computer breaks down and you need to buy another one, you need to buy the exact same configuration because you don't want the differences coming from solely due to the arithmetic architecture in your computer that would affect the numerics in your model. If your computer breaks down, you need to buy another one exactly the same. And if you need to switch to another research center, you need to use a new computer. That's not good. You have to rerun everything from the beginning because you want your, it's like your laboratory, right? You have to use the same laboratory for your experiments. You don't want to switch to a new laboratory in the middle of your research. Okay, so that's how we see our research when we do, so we don't want the numerics to be affected in the middle of your research. But how can we determine the best guess? There's no way to determine the best guess here. There's no way to determine the best guess. So most of the times we would say that if more ensemble members agree with each other, we will use that as our best guess. So that's why we do the average. The average will not give you the best result, but it will not give you the worst result. So that's why when you see when you check, okay, when there's a triple cycle coming, you can see that a bunch of tracks showing in the forecast. Most of the times they just average all the locations from the tracks and then use that as the prediction. The part we need to write by ourselves is just defining Lorentz function. 係咪第二題問題啊？想問。The part we need to write. 哦，都係嘅，都係嘅。但係呢一 part 我就唔夠膽包啦嚇，呢一 part 係，呢一 part 係，呢一 part 你就要 you have to use the new scheme that I've given you. So at this stage, you should be able to code with the equations that you're given, turn that into numerical forms, right? There's no need to turn that into. Okay. Okay. At this moment, you should be able to turn the equations, the differential equations, into numerical forms and then code with that with the schemes that you are asked to do. So this is the job that you need to do. If I give you an equation, not affection, we just learned about affection, right? If you're given a differential equation and you should be able to code, of course, if you're coding with the schemes that you're familiar with, then you'll be faster. But if you're not, then you need to, for example, I've given you the scheme here. You don't need to understand the scheme. You don't need to derive that from the beginning, but you need to code around this. How do you code around this? So try to do that for the second exercise. You don't need to understand, you don't even need to understand the convection, things like this. So this, I didn't talk about this graph. This is showing you the temperature gradient from the bottom to the top. Okay, separate the terms. Okay. I'm okay. Okay. Any other questions? If you have time, I suggest you to watch the video. Watch the video I've put down here, the first one. Of course, you need to look at the first one, but the second one is quite extensive, right? But it's very interesting. It doesn't have a lot of math. And if you're really interested in studying chaos, there's a book here. A lot of applications I've looked at it briefly. Okay, a lot of applications with equations, and you can code for that. A lot of the online videos, they are from simulations. They're not from the true pendulum, for example, here. Oh, there's a video here I found for this Lorentz water wheel. It's the true water wheel. Some people built it, and then it's very fascinating to look at them turning around and changing direction. Okay. Things I would also like to talk about this Lorentz model is that you can see that they deviate from each other, but they never deviate away from the two attractors in here, the 2 points in here, which is very much, I think, in the mathematical world, they call it attractors. So the 2 states here, which is pulling them around them. So it's very much like our climate, because if your temperature is changing a lot, for example, but it doesn't change away from some states. So if you do some statistical analysis, you can see a distribution of temperature, and your temperature only deviate around a certain range. Okay, that is the same idea comparing to this 3 variable model, right? It never deviates too much, and it depends on the different variables, the different properties of your model. Here, the sigma, R, and B. And there are only 2 nonlinear terms in here. Actually, the first one, this one, second one here. So what they call is that it's locally chaotic, globally stable. It's kind of stable, right? It's going around. Okay, 仲有冇問題? Okay, if not, then that's it for this lesson. Thank you.
咪問啊？
問啦，係咪有問題？
係我想問咧 ，D part 嗰度有個 table 嗰度係填數字㗎。
你覺得咧？
應該係啩？
你覺得咧填啲咩啊？好簡單嘅咋，對翻個 scheme 嗰條式填翻落去得㗎啦。Hello， 黃家朗啊，明唔明啊？係咪？
係 OK。
OK 啊？